Hello, everybody. I'm really excited to speak to you tonight. Cool, we got a clicker, everything's good. So for a little context, this is a talk I gave at JSConf Hawaii last week in Honolulu. We're not in Hawaii, so some of the Hawaiian references may be a little bit weird. But if you want to go to Hawaii, I looked at some rates. If you want to do like a last minute Valentine's Day thing, if you leave tomorrow at 10:40 a.m., hang out in LAX for 2 hours, you'll get there at 6:23 p.m., which is actually great because Hawaii is 2 hours earlier than us, so you get a little bit more of the nightlife. Anyway, if this talk gets you a little bit excited about Hawaii, there's your out. All right, without any further ado, this is how to wait. All right, here we go. Our story begins with a familiar await fetch call here. These two lines of code make an HTTP request, wait for a response, and print out the status code of the response. This should be pretty familiar to many of you. While this code's waiting, though, a cascade of activity is taking place in your JavaScript runtime, your operating system, and your hardware. In this talk, we're going to look at what happens in between these two lines of code and what waiting can teach us about software design. Now, you might be thinking, hold up, why do I need to think about this stuff when I'm writing Node.js code? And no less in the middle of downtown Soma, I guess? Well, I was going to say no less like 100 feet from a beautiful beach. But regardless of where you are in your current moment, in your mind, you can be in Hawaii right now. So let's go there. So why do we care about all of this low-level stuff? Well, I can sympathize because I've wrestled with this before. It's hard to motivate yourself to dig into the lower levels sometimes. So I'd like to offer two motivating ideas. First of all, this isn't trivia. Like, these are real systems we use every day while writing JavaScript code. Understanding these systems can teach us examples of how problems can be solved in a more general way. And more importantly, this gives us the opportunity to identify patterns that can guide us to build new systems. Second of all, computers are really complex and powerful, and that can sometimes make them seem magical. Much of that complexity comes from layer upon layer of simple solutions to problems. And as JavaScript programmers, these problems are really relatable to us because we live already in an asynchronous world. By understanding the problems the lower layers of our stack solve, we can gain a greater confidence in the face of this complexity. As you'll see, a lot of that complexity serves a simple task, which is how computers wait. Again, my name is Max. I live in San Francisco. I'm a developer experience engineer at Patreon, which is just a couple of blocks away from here. And thanks for the intro to WaffleJS. I'm a co-organizer there. We get together the first Wednesday of every month. We have 10-minute talks, four of them, on technology, art, creativity, and it's a really good time, so you should come by. Also, one last thing. I'm really sorry, but I have to leave for a prior engagement right after this talk, so I'm not going to have a chance to meet many of you, but feel free to send me a message on the Twitters, and I'd love to talk more. So back to waiting. Waiting is actually a really complex and tricky concept to explain because people almost never do it. We spend as little time waiting as humanly possible. If I ask you to wait for something, what are you going to do? You're going to immediately find something else that's a better use of your time. You're not going to be waiting. When we use the word wait, then, it's usually a concept that we apply in the context of some set of instructions we're communicating. When there's a dependency in a process, we have to wait until like we're no longer blocked. Good recipes take advantage of this idle time by interleaving processes. So when you're blocked on one thing, then you can start on another. This is a great analogy to how computers multitask. Except computers have a lot more going on. They have thousands of different processes they're carrying out at any given time. And unlike most recipes, the order in which things can happen is unpredictable to the computer. As programmers, we like to think in terms of sequential steps because it makes our code simple to reason about. You make an HTTP request, then you wait for a response, then you print out the status. This is why async await style programming is so useful. It lets us express these steps in a clear and linear order. Waiting is what makes that possible. It's the glue that allows us to express a series of separate events linearly. When we say to wait, we expect that the human or computer on the other side is going to find something else better to do in the meantime. This is a behavior we have to design intentionally into our computers. So what we're going to do is dive into the mechanisms of how computers wait, starting with a simple microprocessor. For simplicity, I'm going to focus only on a single core CPU that can only do one thing at a time. I think maybe Rich might be speaking next month about worker threads. Concurrency is a real cool thing that you can do right now in Node.js, but we're not going to talk about that. We're going to assume that a CPU can do one thing at a time because that's all we need to really get into the guts of what waiting means for computers. So come back next month for Rich's talk and come host SFNode. So our story begins with a subcomponent of the processor called the clock. The clock periodically pulses an electrical signal on and off, driving instruction execution. In modern CPUs, we measure the clock frequency in familiar term gigahertz. That means the clock is oscillating billions of times per second. And the reason I'm bringing the clock up is from a reductionist point of view. If you want to think about where waiting starts, waiting for a CPU happens between one clock cycle and another. Nothing happens without a clock cycle on a CPU. So as we dive deep, start building layers on top of this, everything is driven by the clock. So if you start programming a simple microprocessor, you can implement a simple kind of waiting called busy waiting. This is a loop where each cycle you check the condition you're waiting for. But if you want to do other things while you wait, you have to intersperse them in this while loop. And that makes your while loop less efficient, and it increases the time in between cycles. So it's kind of a limiting way to implement waiting. And as you can see, like if we start adding multiple conditions to our while loop, now we have increasing overhead and our loop becomes less efficient. That's where in CPUs, interrupts come in. Interrupts signal the CPU when something happens, such as your network interface receiving data or a keyboard key being pressed. They can also be used for like timers. So CPU can say, hey, let me know in some future time, send me an interrupt. When a processor receives an interrupt, it pauses what's currently running, saves the execution state, and switches to different code called an interrupt handler. The interrupt handler takes any immediate actions necessary and determines how to proceed. The code that implements interrupt handlers is part of your operating system. The operating system makes it possible to write higher level programs that don't have to worry about interrupt handling and communication with hardware. The operating system also governs switching between programs which are running so that multiple programs can share and take turns sharing a CPU. This is called scheduling. The OS also provides APIs for I/O called system calls for things like writing to files and sending packets. In Linux, most kinds of I/O are represented as operations on streams of bytes. Now, I know this may be familiar to all of you, but I want to get everyone on the same page, so now we can dive in and talk about different modes and mentalities for I/O and how that applies to waiting. So I/O takes time. Disks take time to perform operations. Network devices take time to transfer data. When a program's performing I/O, it often wants to wait until that I/O is completed. A simple model for this is called blocking I/O. While a program is waiting for an I/O operation, it's going to take some time. We say the calling program blocks until the I/O completes. Once the OS receives an interrupt that the I/O is completed, the process is queued to be resumed by the scheduler. When a process is blocked, the operating system can then go ahead and run something else. Simple blocking I/O system calls only wait for one thing at a time, though. If we wanted to wait for multiple things, we're going to need to add some additional tools. This is one reason operating systems provide non-blocking versions of many I/O calls. So let's take a look at one. When you open a file or network connection, the operating system returns a number that identifies the stream. This is called a file descriptor. You can then use that FD to reference the stream in other system calls. If an operation would block, a non-blocking read returns an error instead. It says, hey, I know you wanted to read from this, but you actually don't have any data, so here's an error instead. If we get that error, that means there's just nothing left in the buffer, so we can do something else instead. And the reason why non-blocking I/O is cool from the programmer's perspective is that instead of forcing us into blocking and pausing the execution of our process, it lets us know, it keeps our process running, and then we can decide what we want to do. So we can build higher level things on this. This allows us to, for example, wait for multiple things at a time. So let's say we have a list or an array of file descriptors. We can loop over them and try to read from each of them. And if there's no data to read in one, we can continue on to the next one. But if you take a look at this and you kind of like blur out your eyes and think about a couple slides back, it really just looks like busy waiting again. What we really want to do is be able to block on a set of things that could happen to a set of file descriptors. And then let the OS pause our process and wake us up when something that we're interested in happens. Operating systems happen to provide event-based I/O system calls for this. A simple example of this, one of the earliest ones, is called select. Select, you pass in 3 sets of file descriptors, one for each kind of event. Streams that are ready to read, streams that are ready to write, and streams with errors. The select call blocks until an event happens to any of those file descriptors, or like a timeout, specified amount of time elapses. Select then returns which file descriptors can be read, written to, or have errors. And I'm simplifying the interfaces a little bit from their C equivalents, just so that they fit on a slide and we can talk about them. Kind of translating this into JavaScript, because that is a language that we all know. So here's an example of how select works in simplified form. We pass select a set of file descriptors we're interested in reading from, and it blocks until one or many of them become readable. When select returns, it gives us a list of the files which now have data available to read from. We can loop over them and read from them without blocking, because we know that they have data waiting in their buffers. Each OS provides a slightly different modern implementation of event-driven I/O. And this is where it gets kind of interesting. Linux is called epoll, but macOS and BSD have one called KQ, and Windows is kind of different and called IOCP. We're not going to dive into the weeds of these, but what I want you to understand is that if you're trying to write cross-platform software in today's world, you have to implement different I/O code for each platform that you're running on. Some programs do that, and older programs like the Mozilla code base, they had to do that to exist in the era of software development that they were born in. But more contemporary software often builds on libraries that abstract over event-driven I/O. And one that you may be familiar with is called libuv. Libuv abstracts over the varying implementations of event-driven I/O in different OSs and provides a common interface for them. Libuv is used by Node, and Node is built on top of libuv. And we're going to use Node as our example JS runtime in this discussion of how JavaScript waits. It applies to other Node implementations. If you look in the browser, there's a similar framework on top of event-driven I/O, but we're going to focus on Node. We're Node developers after all. At the conference, I called out that there may be some libuv developers in the audience. I'm not sure if there are any here, but if there are, give them a high five. Libuv lets you perform network and file I/O operations and register callbacks when events happen. Libuv uses the operating system's specific event-driven constructs to wait for events. And when something happens, libuv executes the registered callback and then resumes waiting. This is called an event loop. And we're going to dive into an example here. So starting off, to make a network connection, we initialize what libuv calls a handle. Libuv uses the term handle to represent I/O objects that you can perform operations on, like TCP connections. When we open a network connection, we pass libuv a callback to run when the connection is established. This is similar to assigning a callback in JavaScript code. To read data from the connection, we need to tell libuv to track when the connection becomes writable. We provide a callback, which will be called with data, actually readable, sorry. We provide a read callback, which will be called with data as soon as it becomes available. And finally, there's this while loop at the end, which is like a really condensed version of all of the wait loops we've been looking at so far. We run libuv's event loop, which is going to block until any of the I/O events we've asked it to wait for happens. And libuv is going to take care of calling the callbacks that we've registered to handle those things. So we've made it all the way up to Node.js. Node.js is built on top of the libuv event loop. When JS that you're writing, that you're executing inside of Node, uses a Node API to perform I/O, under the hood, Node calls libuv to perform it. And when I/O events happen, Node runs callbacks or triggers events in our JavaScript code. So we've made it all the way through the stack. Now that we've got our cast of characters, let's return to this example code. In order to make an HTTP request, we actually have to perform many different network operations. We have to look up the host name of our destination, open a socket to the IP address of the host, send an HTTP request, receive data, all sorts of things. I'm going to simplify this a little bit so that we can look at just a very narrow slice of waiting. The slice that we're going to look at is a single walk through the layers as we establish our initial socket connection. Starting with our first line of code, await fetch jsconf.hi.com. I was thinking of another 8-letter domain to throw in here, but I couldn't come up with one. SFNode is 6 letters, which is shorter. So let's start with this fetch call. Under the hood, fetch uses Node, at least Node fetch, uses Node's HTTPS module to start the request. It also creates a new promise object, which represents the pending state of the fetch response. Our JavaScript code here is waiting for that response, and it uses the await syntax to pause execution, which causes Node.js to save the state of our JavaScript code and switch to running other queued up callbacks or event handlers. We're going to skip over, as I said, some of the complexity here, like doing the DNS lookup, and dive straight into Node using libuv to open a connection to our destination address. Node queues up a callback to run when that connection is established. To accomplish this, libuv tells Linux to make the connection. And then at this point, Node will finish running through its queue of other event handlers and callbacks to run. And when Node is out of things to run, it needs to wait for new IO to happen. So Node calls libuv's event loop, waiting for the next IO event. Under the hood, libuv is using the Linux epoll API to track these IO events. Libuv says to Linux, hey, I'm interested in when this socket becomes writable. Then libuv under the hood, to actually perform the waiting, will call epoll pwait, which is Linux's epoll API for waiting for the next event to come in and blocking the process. In the meantime, there's some stuff happening under the hood. Linux is using its network stack to make the connection. Linux's network driver sends data to the CPU, and the CPU transfers that data to the network device. And this is going to go back and forth until we eventually get an interrupt from the CPU that's a response coming back from the network interface. The interrupt is going to cause your OS's network driver to read data from the network interface, and this is going to go happen a while back and forth as the connection is being established. Finally, eventually you get that synac call, that magic synac packet that means that the network connection is, both sides are agreeing, hey, we've got a network connection. And the OS represents that as the socket becoming ready to write. Remember how the OS represents most IO as streams of bytes? Well, the stream abstraction, you say, hey, if once a connection is, we bundle up all this like state about a connection being established and just represent it as a stream. And when that stream is, that connection is established, that stream becomes ready to write. So that triggers our epoll wait to finish because an event has happened on something we're interested in. libuv takes that event, processes it, and says, oh, we've got a callback waiting for the connection of this socket. So libuv calls into Node, and Node's uv run iteration finishes. Node is going to take it from here and carry out many additional steps to establish an HTTP connection with our socket. It's going to need to do a TLS handshake. It's going to send down HTTP verbs. We're going to skip over that and just get to the point where in Node's HTTPS module, we get a response event from the request that we made. That's going to cause, under the hood, Node fetches promise to resolve, which is what our await was waiting for. So Node is going to restore the JavaScript execution state and then continue from where we left off, now with a response object, and it's going to print out the status code of that response. So that was a lot to digest. Let's take a little breather for a second. One thing that blew my mind at JSConf Hawaii is one of the speakers, before they started their talk, they had everyone do 10 squats. I'm not going to have you do that. But I want your minds to do that right now and think about how relaxed you'd be after doing that. So let's look at the key parts here in one picture. Your JavaScript code awaits a promise. Node.js accomplishes this by pausing execution until the promise resolves. Node uses libuv to queue up network operations. Libuv uses the Linux epoll API to listen for events. And then we hand it off to the CPU and the operating system. But there's a question here that I haven't answered, which is where in this process are we actually waiting? Remember how waiting is this kind of weird, difficult to pin down concept? Well, where does waiting happen in this picture? The first 3 steps are really only creating information. When the request finishes, resume my JavaScript code. That's information. When the connection is established, run my libuv callback. We're not actually waiting here. We're just queuing up things and defining relationships between what we're waiting for and what to do when it's ready. On the other hand, the operating system and CPU are responding to real-world events and executing the code that's queued up waiting for them. Let's recap and summarize what's happening when our JavaScript code waits. Together, our JavaScript code, the Node.js layers, and libuv layers, they perform I/O and queue up handling the responses. They put what we want out into the world, and they say, hey, when this stuff comes back, this is the queue of things that are going to happen. The operating system juggles incoming I/O events that happen in the real world and runs processes as they become unblocked. The CPU executes instructions while being interrupted as real-world things happen. Intuitively, this is kind of similar to how humans wait. We keep track of what we're waiting for, and we do whatever we're not blocked on until something new, interesting happens and interrupts us. I want to dive a little bit more into CPUs before we wrap up. CPUs are really interesting because we've thought about them so far as a black box, but they actually have their own very advanced waiting constructs. They can perform many things in the background. One example is DMA, which is a subsystem that transfers data between devices and memory while the CPU is doing other things. When a transfer finishes, so the CPU says, hey, transfer this data from this memory address in this device. Go do that. And then the CPU starts executing other instructions, and eventually an interrupt comes back from your DMA controller saying, oh, the transfer is completed. So it's really, you can think of it like a callback in JavaScript. The CPU makes a request, the request happens in the background, and the CPU is notified when it completes. CPUs can also, as I referred to earlier, they can set timers to trigger an interrupt at a specified time using they often use a subcomponent called the high precision event timer. This is analogous to set timeout and set interval in JavaScript. The CPU can set background triggers to fire after some time has passed. When work is happening in the background, sometimes the CPU actually doesn't have anything to do. So how does the CPU wait? The first thing CPUs can do is lower their clock speed. This reduces the amount of power the CPU consumes and the amount of heat it generates at the cost of slower execution. The second thing CPUs can do is progressively turn themselves off. In a modern Intel or AMD CPU, a core can issue what's called a halt instruction. This is going to cause the CPU to stop executing instructions until an interrupt is received. This allows the CPU to power parts of itself off, and this saves your user's battery life. As an aside, this is one reason why on the front end, request animation frame is awesome. Front-end JavaScript code often uses request animation frame to queue up and schedule animation timers. And as you can see, I think animations are awesome personally, but it's a good idea to use them sparingly to save your user's battery. And one thing that request animation frame does that's kind of cool is it can reduce the frequency of the animations or skip them entirely when you're low on battery based on your browser's preference. And this enables CPUs to enter powered off deep sleep states. Now, back to waiting. If we look at how waiting is accomplished at each layer of the stack, what we're trying to accomplish and how we accomplish it at each layer kind of bears a resemblance. Each of Node, libuv, and the operating system scheduler consume incoming notifications that something happened. They then dispatch handlers to respond to each incoming event. And then when there's nothing left to do, the loop sleeps until new events are available. In a nutshell, we're running in a loop. We consume a queue of incoming things, and then we wait until more are ready for us. This is where the name event loop comes from. If you squint, both the operating system and Node.js appear to be doing kind of similar things here. The operating system enables programmers to write linear blocking IO. Node.js, on the other hand, enables developers to write linear sequences of IO using callbacks or async await code. Both the operating system scheduler and Node.js's event loop allow multiple sequences of code to be interleaved. This is why we like them. But there's a difference between these two systems, which is that the operating system implements what's called preemptive multitasking. That means if a CPU interrupt occurs while a process is running, the operating system can pause that process and switch to another. It actually forces that process to pause. The operating system scheduler uses a timer so it can regularly interrupt processes that are taking too long so that they don't hog the CPU. Each process there gets mostly a fair share of CPU time. As you might be familiar in JavaScript, that's not the case. We use what's called cooperative multitasking. The event loop only runs in the spaces between your JavaScript code executing. Your JavaScript code can and will delay the event loop from handling events. And this is a deliberate design choice. It actually gives us a fair amount of power and control as JavaScript developers. While your code is running, incoming IO can't interrupt or change the state of the JavaScript world, which is useful to us. And it also gives JavaScript code the ability to choose exactly when it wants to yield to the event loop. Are you busy? Are you actually computing something that's really important? Well, you're not going to get interrupted, at least not by Node.js. Your operating system, on the other hand, might have other ideas. So then you might be wondering, like, okay, we've got all this cool stuff in Node.js. Why do I need an operating system to have this additional layer of context switching? Wouldn't our code be more efficient without it? Well, it turns out it would be, but you lose a lot of generalism that way. Our computers are usually doing more than just running JavaScript code. You know, we have Slack, and I guess Slack is written in JavaScript. I guess, I don't know, Bash, Git's not written in JavaScript, so we still need the operating system for that, I guess. It is, however, possible to eliminate the OS entirely and build runtimes that operate directly on the CPU and hardware. These are sometimes research projects. It's referred to as unikernels. They're really cool. I actually researched one for this talk, but it's not maintained anymore. So I don't have a ready JavaScript unikernel to point to. But if you're interested in it, give that term unikernel, UNI kernel, Google, and it's really fascinating. But yeah, in general, we want our computers to be able to do different kinds of things like running Git, and you can't do that in just JavaScript. Maybe Emscripten could get you there. Maybe with WASM someday, but an operating system in 2020 is still pretty useful. So what if we instead got rid of the event loop and instead let the operating system schedule blocking IO? What do we need this event loop for anyway? Couldn't we just run a bunch of processes? The answer, as some of you may be familiar with, lies in economies of scale and the difficulty of scaling up multiple process and multi-threaded software. Each operating system process has a constant amount of overhead in terms of the memory that it costs. And it also takes time to switch between them when we save and restore the execution state. In contrast, by using event-driven IO in an event loop, a single process can manage a vast number of async IO operations in bulk. The overhead's lower because the single process can use more compact data structures for keeping track of state. The event loop can also exert finer-grained control over the priority in which it handles different events compared to the operating system's more general-purpose scheduler. So what does this all have to do with JavaScript, and what does it have to do with waiting? Most interactive applications can be thought of as a tapestry of event-driven code. We weave together a sparse graph of code that runs in response to external IO events happening. In between these short bursts of activity, our programs are most of the time just waiting. A great abstraction breaks down a complex problem into multiple simpler pieces. Blocking style IO enables us to think about this tapestry as linear flows of events. This is what makes Node.js and async await syntax such powerful tools. They give us leverage over this complexity. Under the hood, the event loop ingests an unpredictable stream of incoming events, and it advances the linear flows that we've defined as programmers. Great abstractions also tend to make both sides of their problem space more efficient. Blocking style IO not only helps programmers understand their data flows, it makes explicit what our processes are waiting for, so that the runtime can focus its attention elsewhere. And yet, abstractions always leak, right? What we do in our JavaScript code has impacts across the entire system, even though sometimes we have limited control over it. As our stack of abstractions grows, the distance between what we intend to happen and how it happens widens. Before we wrap up, there's two newish layers of the stack we haven't gotten to that are pretty interesting. One's on the back end and another's on the front end. If your backend code is running in the cloud, it's actually not running on a real CPU. Surprise! The Matrix is currently filming in San Francisco, so I have to give a shout out to that. There's an additional virtualization layer, and it provides a virtual CPU, not a real CPU. And the software that does this is called a hypervisor. The hypervisor has its own scheduler, which is allocating CPU and IO time based on what you're paying for. Now, on the front end, just going to touch on this very briefly. It's kind of interesting because React, in its more recent versions, 16 and above, is implementing its own scheduler called React Fiber. Because the event loop doesn't have a way to preempt control from JavaScript when it's taking too long, React Fiber slices up what it's doing into small enough pieces to run in between individual frames, so it doesn't delay the browser rendering the next frame. So React Fiber is another scheduler that your JavaScript code on the front end is interacting with that splits up large UI re-renders into smaller pieces of work. And one of the advantages of that is that Fiber can then prioritize time-sensitive work like updating input elements. Wrapping up, there's a tendency for us to think of high-level programming languages like JavaScript as less efficient because they introduce additional layers of overhead and less control over execution. I want to leave you with a more nuanced idea than that. As we've seen with waiting, working at a high level of abstraction often leaves you with a clearer expression of what you're writing. The more clearly programmers can express their intentions, the more information we can weave into our tapestry of events, and the more latitude we provide our execution layers to optimize them. The real cost of adding too many layers is mismatching abstractions. where we waste energy translating one problem into another. As you've seen, many layers of modern computers provide means of waiting in similar ways. Over time, we're going to simplify away some of those layers and specialize them to better serve the needs of modern applications. At the same time, we can expect that the future is going to demand even higher level languages or high level abstractions built in those languages, such as React. As you've seen, JavaScript gives us tremendous leverage over the OS and CPU to weave together flows in a way that's intuitive to us as developers. But programming is still a young medium, and it's important to stay humble, right? We still have a lot to learn about how to structure our ideas, and our children are probably going to figure out some really cool things that we haven't even thought of yet. So if you're interested in diving in deeper, there's 3 awesome resources I'd like to recommend. You don't have to take a picture of this. I have a link, a URL for this slide on the next slide. But Sam Roberts' talk is awesome. It talks about how the event loop works from the inside out at a C level. So he talks through the actual implementation details of what Node.js event loop is doing. Cindy Sridharan's article on Nonblocking IO talks about how Linux under the hood implements the epoll API and event-driven IO. So that's kind of the other side to what you're doing and interacting within your Node code. And finally, Marek Machkowski's blog post on Select One, and it's actually a whole series. It walks through the history of how IO multiplexing happens in early computer systems, while they were still figuring it out as they went along, building networked computers for the first time, and thinking like, what if I want to wait for more than one thing at a time? Really fascinating, and he does some cool historical work there. And actually, I think he has an exchange with Rob Pike, and asks some of these living legends, hey, what was the deal with this? Really cool. So with that, I'm going to yield back to the SFNode event loop. Thanks for scheduling your attention with me.